Today I'd like to talk about continuous delivery and what good looks like in software development. It may or may not surprise you to know that I think those two things are pretty close to synonymous. I was involved in writing a book about continuous delivery some time ago, which helped to popularize the idea. But since then, we have a lot more experience of the practice of it. So what is it that you think about when you hear the phrase continuous delivery? Maybe you may think of the book that I was involved in writing, and I'm kind of pleased if that's the case, but there's more to it than that. And maybe if you're a bit deeper in, maybe you're thinking in terms of the State of DevOps report and the Accelerate book that came a few years later, which enumerates a detailed scientific justifiable investigation of what really works in terms of software development practice, and it turns out that that's largely around continuous delivery. Some of this research has been ongoing for nearly a decade now, and the results of today's State of DevOps reports is completely in line with what we learned nearly a decade ago from this scientific investigation. If you haven't read the Accelerate book, or my book for that matter, I recommend them to you. At the heart of the Accelerate book is the idea of two key metrics which are used to evaluate software development performance, and then a valid sociological technique for gathering data and proper statistical techniques for analysing that data and understanding what it means. The first of the measures are based on throughput, and we measure throughput based on lead time, how long it goes us from committing a change for that change being ready to go into production, and frequency, the frequency with which we release changes into production. And this is a measure of the efficiency of our development process. You could say, with some justification, the speed of our development process. The second group of measures are based on stability, and stability is measured by change failure rate. At what rate do we introduce failures into production when we release change into production, and the time it takes to recover from those failures once they're introduced. This is a measure of quality. And one of the profound things that the State of DevOps report found is that despite many people's prior conclusions, there's actually no trade-off between speed and quality. In fact, it's completely the reverse. If you want to build software quickly, you must build software with high quality. If you want to build software with high quality, you must work quickly. That is to say, in many small, frequent steps, rather than fewer, bigger, more complicated, slower steps. And there are profound reasons for this, but the obvious way to recognize that this is true is, let's imagine that I make some changes to my software this week and introduce a load of mistakes because I'm working with low quality. Next week, I'm going to be working on new things, hopefully, but I'm also going to be spending an awful lot of my time addressing the problems and fixing the problems that I introduced in last week's work. So I'm going to go slower. And that plays out dramatically in software development. And you can see there are often orders of magnitude difference in the measures of low performers versus high performance on these metrics. So there's no trade-off between speed and quality. This surprises lots of people, and it has profound implications for how we should work and what we should do to achieve a good result. The nature of the problem is interesting, and I've taken this from a book called The Art of Action by Stephen Bungay. If we have some kind of outcome that we'd like to achieve, then we're going to make some plans to be able to figure out how to achieve that outcome, and then we're going to carry out some actions to that plan, and hopefully we're going to achieve our outcome. The problem with this is that there are some gaps. The first gap is between outcomes and plans, which is the knowledge gap. There's a gap between what we'd really like to know and what we actually know. And then there's a gap between plans and actions, which is what we'd like people to do when we make a plan and what they actually do. And then the gap between actions and outcomes, the effects gap, which is the outcome that we expected to achieve and the outcome that we actually achieve, which aren't necessarily or even usually the same thing. The classic responses to dealing with each of these gaps, which are profound whether we acknowledge them or not, and pervasive, is first, for the knowledge gap, is to plan harder, analyze more, do more detailed requirements. Now, there's a big problem with this based on the information from the State of DevOps report, because this means going slower, and as we've already seen, slower means working with lower quality. So that's not a good result. The alignment gap similarly has a series of what we might think of as traditional responses. Micromanagement, process control, added bureaucracy, and once again we go slower, and that means lower quality. And finally, the effects gap is also a problem. So for this, classically, what organizations have done for decades now is expectation management, under promise and over deliver, watermelon status reporting, it's green on the outside and red in the middle, and increasing project management rigor. And once again, this means that we go slower, and that means lower quality. So none of these things are the answer. None of these things are what work for us to be able to do a better job, to do a good job of software development. But it's worse than that. It's not just that we're going slower, but we must do these things together. If we go slower, we build worse software slower. So the outcome is bad all around. We want to be able to deliver software more quickly, more frequently. That's what nearly every organization demands of software development teams. But when we do the things that the organization assumes are going to be the right things, they make the situation worse. This is a vicious circle that software has inhabited for probably the last 40 years at least. There is an answer though. Although we can't close these gaps, we can work to reduce them. And we can do that by speeding up. If we can't eliminate these gaps altogether, we can reduce their impact by working in smaller steps. And this is profoundly what continuous delivery is all about. The continuous delivery book also talks about working so that our software is always in a releasable state. This is my favorite description of what it is that we mean when we talk about continuous delivery. We're trying to optimize to ensure that after every small change, our software is still in a releasable state. That means that we need deep insight into the state in which our software is in and whether it's releasable or not. And that means optimizing to be able to work in these small steps that allow us to optimize overall to achieve better outcomes and discard the steps that don't work and keep the steps that do. And part of that game is trying to make sure that we are always evaluating against something realistic, which means our software must be releasable. That's the definition of real in this context, in the context of continuous delivery. So what kinds of things determine releasability? The key idea that much of Jez Humble and my book on continuous delivery explores in some detail is the idea of the deployment pipeline. There's more to continuous delivery than only deployment pipelines, but deployment pipelines are a crucial enabling technical strategy to achieve the goal of continuous delivery, which is maintaining our software in a permanently releasable state. The idea is that we're going to optimize to evaluate the software to the point of releasability after every small commit. And by small commits, I mean multiple commits per day per developer. The idea is we're going to evaluate our tests locally to support the development process and get fast, instant almost feedback in our IDEs or in our text editors that the software that we're doing passes the tests that we're working on right now. We're going to then evaluate that slightly more formally. Everybody else's changes evaluated together with ours after every small commit by any team member for any change that's testing for production. And we're going to evaluate those changes and give very fast feedback. And that's fundamentally looking at, does this code do what I as a developer think the code should do? That's really valuable, but not quite enough. So we also need to know, does this code do what the users want to do? So we're going to use techniques like BDD, acceptance test driven development, to create executable specifications that define the releasability of our software from the perspective of a user of the software. And then there are other things that, depending on the nature of our software, we might be interested in. Is the system nice to use? Is it fast enough? Is it resilient enough? Is it scalable enough? Is it secure enough? Is it compliant enough? All of these things might come to play. Whatever it is that we think determines the releasability of our software, that's stuff that we should be measuring in the scope of our deployment pipeline. If all of these tests pass, that means there's no more work for us to do before we're comfortable for release. So our software is releasable. The deployment pipeline is definitive for the releasability of our software. That's our goal, and we want to be able to achieve that frequently. We want to get that feedback quickly. Continuous integration is a fundamental core strategy of continuous delivery. I get a bit grumpy when people talk about CI/CD because it's just CD. CD is continuous integration, only taken further. So our idea is that after every tiny change, multiple times per day, per developer, we evaluate the releasability of the system to the point where there's no more work to do before we're comfortable to release that change into production. So we're going to commit some change. We're going to generate a release candidate, which is a deployable unit of software. We're going to evaluate that based on all of the things that determine its releasability. And then if all of these tests pass, we're ready to go into production. Now, this doesn't prove that our software is good. Nothing can prove that our software is good in reality. This is a much stronger statement than this. This proves that when our software is not good enough. If a single test fails, our software is not releasable. That's the game. That's how science works. That's how engineering works. We're not attempting here to prove that our software is good, because that's a kind of fool's errand. You can't prove these things. We may always have missed something. There might be some tests missing that we didn't think of. There might be some circumstance that we didn't think to simulate. But however many tests we've got, however few tests we've got, if one test fails, we know that that system is not releasable. So we can use the deployment pipeline as a falsification mechanism, which is a much, much stronger statement. This allows us to be much more confident in how we can make progress. We gain confidence by testing our system thoroughly, by sampling it sufficiently that the chances of us missing something are reduced. They're never reduced to zero, but they'll be reduced. And if we're looking to test thoroughly, that fundamentally means automated testing. We want to be able to run thousands, tens of thousands, potentially millions of tests after every commit. I think of this as a genuine engineering discipline for software development. True software engineering, really. Part of that is that we're optimizing for learning. We're trying to organize the way in which we approach software development so that we're able to make mistakes. We're free to make mistakes, but we can make mistakes safely. If I commit a change and that causes a test to fail, it means that I'm blocked from releasing that change, and now I can go think more carefully, more deeply, maybe add some more tests and figure out why that change is dangerous and fails the test. Or maybe the tests are wrong and I can correct the tests at that point. This is a much stronger statement of the releasability of our system. So if we're optimizing for learning, there are some other things that we can think about. We want to work iteratively. That's the small steps thing. We want to be able to carry out each change as a series of small steps. That gives us multiple facets. Amongst other things, it allows us to better control the variables, but it also allows us to gather feedback and understand from that iteration the impact of our changes and whether they're good or bad. We're going to make incremental progress. We're going to treat software development as a kind of evolutionary process. We're going to evolve our software step by small step over time, gathering feedback through iteration and validating that the current state of the software is good and releasable. Incremental development. We're able to go back and change the software at any point. We're going to work in an experimental way, which means that we're willing to take risks. We're happy that if things break, as long as they break in controlled circumstances, because at the moment when they break, at the moment when one of our experiments fails, that's when we're learning more. If we make a change and it's not fast enough, and our performance test says it's not fast enough, now we're learning how to write better code, whether to optimize for greater performance, or whether the performance criteria that we'd set ourselves were unrealistic. But either way, we're learning. And finally, if we're optimizing for learning, we need to be empirical. We need to be thinking about the real world impact of our software and what works and what doesn't, what scales and what doesn't, and learning from production as well as learning from the more controlled circumstances within our deployment pipelines. The other aspect of software engineering in these terms is managing complexity. We build systems of vast complexity these days, and so using techniques to be able to manage that is vital to our ability to sustain the pace of change and the quality of our work. We want to be able to make changes in one part of the system without it automatically impacting other parts of the systems. We'd like to be able to evaluate those changes more independently of one another. And these are all down to the techniques of managing complexity. I have another 5 things in this category. Modularity. Modular systems are more testable, they're more readily deployable, they're more functionally capable usually, because we can use them in different ways, because we can reuse modules in different contexts surrounded by other parts of the software system. We want to use abstraction to be able to interact with other areas of the system, but in controlled, well-defined ways, so that we can make changes in another part of the system without changing the software in the area where we're working, or vice versa. We'd like to design software with better separation of concerns, where each part of the system is focused on doing one job well, one part of the solving one part of the problem, and not conflating lots of different parts of the problem together, which makes the software more difficult to work with. We prefer software that's generally trending towards being more loosely coupled. It's not quite right to say always strive for loose coupling. Better to say we should be managing coupling to an appropriate degree given the nature of the software, but with a preference for as loosely coupled as is sensible in all the rest of the context. And finally, we want software that's more cohesive, so that the parts that are closely related are close together in the code, and the parts that are unrelated are far apart in the code. That's a pretty good, each of those is a pretty good definition of cohesion and respectively modularity. These 5 things for managing complexity are fundamentally important because what they give us is that they maintain the ease with which we can make changes to our software, and that's important because that's what allows us to go fast. That's one of the things that allows us to work with speed, efficiency, and as we've already explored, that's one of the things that gives us higher quality outcomes. The deployment pipeline is built to service this and to optimize to give the earliest feedback. So we have some developers, they commit some change to a version control system, and that goes into a commit stage where it's evaluated. And the job at this point in the life cycle of the change is to give fast feedback that supports the development process. We want the developers to be able to make a change, get a quick, close to definitive view on whether the software is releasable or not, and then move on to something new. Now, there are things that we want to evaluate that take too long to do that. So the deployment pipeline is consciously divided up into a series of different parts. The first part is what I call the commit cycle. This is the developer supporting part of the pipeline. And the idea of the commit cycle is to give very fast feedback back into development teams. We want ideally feedback in under 5 minutes following a commit. That gives us a fairly high level of confidence that if all of these tests pass, everything else is going to be good. This means this says something important about the nature of the testing that we can afford to perform at this point, because it's got to be fast. And so that probably means we can't afford tests that talk to a real database, talk to disk, start new processes, talk to something across the network. What we're talking about is in-memory tests that we can run in parallel with each other, certainly for a larger system, and potentially run hundreds of thousands, maybe millions of tests within that 5-minute window. That's perfectly possible as long as these tests are simple. This is largely, if you're thinking test-driven development now, you're on the right track. These tests are best produced as a function of test-first, test-driven development, because that's how you write tests that are that fast, that efficient, and that isolated from the infrastructure. The next stage of the pipeline is the acceptance cycle. And the acceptance cycle is about what I was doing what I was talking about earlier, which is evaluating the releasability of our change. Does it do what the users want it to do? Is it fast enough, resilient enough? All of those things that we talked about. And whatever it is that your software needs to determine its releasability, our aim is to try and achieve that through automation to a large degree. You can see in my picture here, I do have a manual test environment, but that's largely just to test that the software is nice. We're not really using manual testing as regression testing. I think manual testing is a very poor form of regression testing. It's not repeatable enough, it's not fast enough, it's not reliable enough, it's not scalable enough. And so automated testing does a much better job of regression testing than manual testing. But manual testing tests some other things, and that they may be useful. If all of these tests pass, there's not much more left to do other than we're ready to release it. Now, we don't have to release our change into production at this point, but the production cycle is all about managing that part of the release process. Depending on your problem domain, depending on the nature of your software, it might make sense to push change into production fast, frequently, all the time on an automated basis when the deployment pipeline says it's good. That's actually a step on from continuous delivery. It's called continuous deployment, but it's a type of continuous delivery. Continuous delivery is working so our software is always releasable. Continuous deployment is pushing the change into production all of the time as soon as our pipeline says it's good. For some kinds of software, that's not really appropriate. For other kinds, it's ideal. If what I'm talking about really was software engineering, it would improve the quality and efficiency of our work. That's what engineering does in other engineering disciplines. That's what we'd expect from an engineering discipline. And that's what it does. Based on the measures of stability and throughput, remember, these are measures of the efficiency with which we deliver software of a certain quality and the quality of that software. These are things that are generic. They are true for every kind of software. They're relevant to every kind of software. And high performers and elite performers on these scores do dramatically, orders of magnitude better than low performers. That's what good looks like. Good looks like building better software, higher quality software more quickly. The impact of continuous delivery, as we've learned over the decade and a half or so since Jez and I popularized it with our book, has been profound. I think without a shadow of a doubt, more profound than either Jez or I anticipated. Things like saying high performers spend 44% more of their time on new features than low performers on the scales of measuring a continuous delivery. There are lots and lots of organizations that practice continuous delivery these days, and many of them are not the kinds of organizations perhaps that many people would think about. I often get pushback saying, oh yeah, all this sounds fine, but it only works for small systems. No, Google do continuous delivery with billions of lines of code, or it only works for simple systems. No, SpaceX builds space rockets. So these are just some examples. I could tell you a remarkable story about each and every one of these companies, and there are many, many, many more. Many of the leading organizations in the world that we think of as high performance in software development are continuous delivery organizations. But here are just a few ideas, thoughts that kind of spring from the experience that we've gained since continuous delivery became more popular. Amazon, for example, practice trunk-based development. They release 1.5 more than 1.5 changes every second into production. They have automated deployment and monitoring. Suspect changes are automatically rolled back with no human intervention. And they operate a kind of advanced canary release process of rolling changes out in waves, releasing first to less risky environments, and then only if they demonstrate their suitability to more increasingly riskier environments until they're rolled out around the world. Volvo were reasonably early adopters of continuous delivery in their trucks division. A modern Volvo truck has millions, I think 18 million plus lines of code in it, and everything from hardware devices in the truck to sophisticated software systems, auto driving and so on, stability control and so on. Before Volvo adopted continuous delivery, it took them 6 months to get a single line change of code into a truck on a test track. After they adopted continuous delivery, it now takes 20 minutes, less than 20 minutes, to get a change of any kind into a truck. This is dramatic and impactful on their ability to build better and better software. Siemens Healthineers, in one of their teams, adopted continuous delivery to build medical devices. These are devices that can kill people if they go wrong. This is a heavily regulated industry, as you might hope for if you're using one of their devices, I suppose. These are safety critical systems. Siemens Healthineers use a sophisticated site reliability engineering approach and full-blown continuous delivery. And they're currently working towards fully automated regulatory compliance as part of this. This is a good book on SRE in particular, but it also touches on the philosophy and application of continuous delivery in complex safety critical systems. SpaceX operate full continuous delivery with test-driven development and trunk-based development for the most advanced space rockets on the planet. They're updating changes to the software in their space rockets up to 40 minutes before launch, and doing that in full confidence that the commit and the validation in the deployment pipeline is sufficient for the relaunch of the multi-million-dollar software space rocket still to be safe. LMAX Exchange is a company that I worked for, building one of the world's highest performance financial exchanges. This was a company that pioneered some of the ideas of continuous delivery and is one of the projects that was source material for the continuous delivery book that I wrote. This was built from day one with continuous delivery in mind. LMAX operates a process of continuous regulatory compliance. It's harder for LMAX to release a change into production that is not regulatory compliant than it is for it to release one that is, because the deployment pipeline asserts regulatory compliance. LMAX also did microsecond resolution performance testing and multi-levels of security testing, resilience, scalability, and lots of other forms of testing in this complicated piece of software. When we went into production, it was 13 months and 5 days before the first user noticed a production bug. That's another aspect of what good looks like. The HP LaserJet team were continuous delivery pioneers. They were in a bad place before they adopted it, spending only 5% of their global development efforts on building new features. The rest of the time were fixing bugs, porting changes, and so on. They changed the way that they're working and adopted continuous delivery practices and became dramatically more successful. The bottom line was that they were producing way more software than before and spending 8 times as much effort on new features than they were originally. That's still only 40% of their development effort. They're spending a lot of time on testing, evaluating things, building deployment pipelines, and so on. But those are an investment in productivity. This is how you go faster. This is the engineering discipline. This is like using tools to measure things rather than just crossing your fingers and guessing. The story behind this is captured in this book, which I recommend, A Practical Approach to Large-Scale Agile Development by Gary Groover and his colleagues. Tesla decided that they wanted to upgrade the maximum charging rate for the Tesla Model 3 car a year or two ago. It was going to go from 200 kilowatts to 250. Now, this involved a physical change in the design of the charging mechanism, but the Tesla factory is a software-driven artifact, and Tesla are a continuous delivery company from start to finish. So what was involved in making this physical change to the design of the car was a software-driven. So somebody committed the change to a version control system that went through the deployment pipeline, was evaluated, passed the necessary tests to say that it was releasable. The change was pushed out into production, upgrading the factory in this instance. And then 3 hours later, from the point at which that change was committed, the Tesla production line was now producing the new design of car with a maximum charge rate of 250 kilowatts instead of 200. This kind of idea, this kind of engineering practice is simply not feasibly possible in the absence of continuous delivery. So I would argue that we're not playing around here. This is a genuine world-class approach to real practical engineering for software. What we're talking about here is that continuous delivery builds better software faster. And that's what we all want, whatever the nature of the software it is that we're building. Thank you very much. I hope you've enjoyed my talk, and I hope you enjoy the rest of the day. Thank you. Bye-bye.